According to standard logic, the following sentence is true. If I'm the Pope, then Santa Claus exists. Unless it's uttered by the Pope himself, mind you. Well, listen, formal logical systems serve as ways to model reasoning. Because of this, every logical system has its own perks. They always have false positives in a way, which are inferences they validate even though you might find them completely dumb, and or false negatives, which are really intuitive ideas that they're in a way too weak to actually validate. The current standard model of logic is obviously no different, but its false positives are quite problematic to say the least. Either part of a true if-then statement need not have anything in common. It has irrelevant theorems. Because of this, logicians have identified a bunch of paradoxes that, in the end, kickstarted the whole relevance logic movement. So we'll start by dissecting these different paradoxes first. As a heads up, this video will be pretty technical overall, so feel free to pause the video for digestion's sake, or skip some parts that you find less relatable or less interesting at the moment. So yeah, now that it's cleared up, let's begin. Standard logic, whenever B is true, it is true that if A then B. So for example, if Alice rides a car, then 2 plus 2 equals 4. And all that just because 2 plus 2 equals 4. This is called the positive paradox. We can defend this because standard logic treats if-then and even if-then as the same connective. So in this case, it's more like even if Alice rides a car, then it remains that 2 plus 2 equals 4. It's still semantically different in natural language, but it makes more sense when you know that perk of standard logic. As well, in standard logic, whenever A is false, it is true that if A then B. So, for example, if the earth is flat, then Bob goes dancing, all by virtue of the earth not being flat. I hope we're all on the same page with this one. So yeah, this is called the vacuous truth. Here it's because in standard logic, for an if-then statement to be false, it will require us to find a situation where the conclusion is false and the premise is true. But since the premise, the earth being flat, is always false, that means that if the earth is flat, then Bob goes dancing can never be falsified, as we say. Therefore, given it can never be false, that means it's always true. Weird, I know, but yeah, that's technically correct. Another paradox of standard logic is that regardless of A and B, we either have that if A then B, or if B then A, or both in the case where A and B are actually equivalent. So for example, if Charlie likes cats, then Dolly works 9 to 5, or if Dolly works 9 to 5, then Charlie likes cats, or both. Even if Charlie and Dolly have nothing to do with one another, especially not one's schedule at work and the other's preference for pets. Technically speaking, it results from the former two paradoxes. Indeed, given the fact that Charlie likes cats is either true or false, that means either Charlie likes cats implies Dolly works 9 to 5 by virtue of Charlie not liking cats, or that Dolly works 9 to 5 implies Charlie likes cats by virtue of Charlie indeed liking cats, or both if they happen to have the same truth value. Finally, in standard logic, again, whenever if A and B then C is true, then either if A then C, or if B then C, or both. For example, given that if it is raining and I'm going outside, then I take my umbrella, we derive that either if it is raining, then I take my umbrella, even if I do stay inside, or if I'm going outside, then I take my umbrella, even when it's sunny all day. Or both. This one is also due to a mix of both former paradoxes. If A and B are both true, we necessarily have that C is true, and therefore both if A then C and if B then C are true by positive paradox. On the other hand, if say A is false, then if A then C is true by vacuous truth. So the whole conclusion is true by virtue of there being at least one true disjunction. The same logic applies if B is false instead, or if both are false. So yeah, despite my best attempts at justifying these, logicians still call these paradoxes of material implication. Essentially, we see that in standard logic, because of these paradoxes, if-then statements do not carry any kind of cause and effect kind of thing, which is pretty much divorced from how natural conditionals work. So one might wonder, is it a necessary evil? As a master's student in mathematical education, whenever I see didacticians tackle this idea that implications need some sort of causal or chain link from premise to consequence, it's systematically treated as a mere property in act, or worse yet, as a student error. Though errors are generally not seen in a negative light by didacticians, it still shows a conflation I find a little too often for my liking, which is that standard logic is treated as being exactly what valid reasoning looks like. In most sciences, when we see something off, we instantly think, oh, okay, we have to refine our models here. But for some reason, there's some kind of formal logic exceptionalism at play here, which acts as an obstacle to thinking critically about that field, which I find all the more ironic as logic is central to critical thinking itself. This kind of purely prescriptive approach to formal logic is very debatable, to say the least, and don't get me wrong, we do need to specify exact rules if we want to characterize an exploitable logical system, which is exactly what we'll do in part 4. But one must not conflate the rules made to define a specific logical system on one hand with pseudo-universal rules of logic on the other. Historically, standard logic was brought forth in Gottlob Frege's ideography back in 1879, so that prescriptive position implies that no one reasoned properly before 1879. Which sounds a bit preposterous, if you ask me. Not only that, but we can also show that some well-established traditional logics, notably term logic, aka the backbone of logic for about 2 millennia, are in some sense incompatible with modern standard logic. One place where we can really show how standard and term logics clash violently is with the modus derivati syllogism, as Estrada Gonzalez 2020 pointed out. The modus derivati says this: if every M is P and every M is S, then some S is P. So for example, every man is mortal, every man is a mammal, therefore some mammal is mortal. Sure enough, that's pretty sound reasoning, isn't it? However, there are more controversial applications of modus derivati, notably the following. Every Pegasus has wings, every Pegasus is an equid, therefore some equid has wings. Since the conclusion is clearly false, despite the reasoning being valid, this can only mean one thing. One of these premises has to be false. However, both premises essentially say for all x, if x is a Pegasus, then x has some other property. And given that nothing can ever be Pegasus in real life, since there is no Pegasus, these for all statements will instantly be treated as true in standard logic because any false antecedent leads to a true if-then statement in that system. And since x is a Pegasus is always false, regardless of x, we have our vacuous truth. In other words, modus derivati, and therefore term logic as a whole, is practically incompatible with standard logic. To be very clear, term logic and standard logic are both perfectly internally consistent on their own. It's just that they disagree on a fundamental level when brought together like two very rational rivals. Term logic thinks all x is y implies the existence of some x, while standard logic simply doesn't. If you want more details on this debate, it's called existential import. Seeing how such internally consistent and important systems can absolutely disagree with one another, it only makes sense that some logicians actually listened to their guts and decided to formalize how one might find connections between either side of an if-then statement. Instead of calling it wrong just because the standard model doesn't validate that pattern, they decided to actively propose more refined models in order to fix such paradoxes. Historically, C.I. Lewis has proposed the strict conditional, for example, but the alternatives, which I find the easiest to switch to, the most successful in this endeavor, the most thought-provoking, and the most criminally underrated all at once, are called relevance logics. To be very clear though, I'll only focus on one specific relevance system, namely R, and some extensions thereof. Other really important relevance logics include relevant entailment, E, decade entailment, T, base logic, B, and the base of it all, first degree entailment, F.ii. You've probably seen or been that person who's like, I don't learn theorems, I can always derive them if I really want to. In standard logic, hypotheses are basically treated as theorems, as though they're already proved somehow. But because of this, it is impossible to track when one uses a hypothesis, just as calling a theorem can always be bypassed by proving it again instead. In a sense, a theorem is indistinguishable from its proof. For the nerdier among you, that's kind of what combination theorems are about, but I digress. In relevance logics, however, hypotheses are treated as resources, akin to linear logic for those who know about it. Each hypothesis has its own index, which carries onto the indices of all logical formulas derived from them. To illustrate this, we are going to show that if-then statements are transitive. This means given if A then B and given if B then C, you can derive the conclusion if A then C. If you want to prove an if-then statement, you're going to need to suppose A, and from that supposition, derive C. So let's first show how this pans out in standard logic. Okay, well, we can interpret these letters as specific propositions to better understand the proof. Okay, first, suppose that if Bob is a human, then Bob is a mammal. Then suppose that if Bob is a mammal, then Bob is an animal. Now what we want to do is prove that if Bob is a human, then Bob is an animal. To do so, we're going to suppose Bob is a human. We know that if Bob is a human, then Bob is a mammal. But we also just supposed that Bob is a human. Therefore, Bob is a mammal by modus ponens, which is the most basic tool we use for deduction's sake. If A, then B, A, therefore B. That's it. We do the exact same thing on the very next line. If Bob is a mammal, then Bob is an animal. Bob is a mammal, so Bob is necessarily an animal himself. And here we have it. We've proved that Bob is an animal by supposing Bob is a human. So by conditional proof, that's the technical term for this inference, we showed that if Bob is a human, then Bob is an animal, given suppositions that if Bob is a human, then Bob is an mammal, and also that if Bob is a mammal, then Bob is an animal. The problem with this proof is that the origin of each derived formula is completely obscured by not keeping track of each hypothesis used. Compare this to the proof of this exact same theorem in relevance logic R. Here we've tagged every hypothesis with its own index number. 1 for if Bob is a human, then Bob is a mammal. 2 for if Bob is a mammal, then Bob is an animal. And 3 for Bob is a human. We can see that mammalness was derived from hypotheses tagged 1 and 3, while animalness was derived from 1, 2, and 3. The fact that Bob, being an animal, uses 3 in particular, creates a relevance link to the hypothesis tagged 3, aka that Bob is a human. We've actively used our resource or hypothesis that Bob is a human to derive that Bob is an animal. Thanks to this, we can discharge hypothesis 3 in peace to conclude that if Bob is a human, then Bob is an animal, which itself carries tags 1 and 2 because Bob, being an animal, also used 1 and 2 when we proved it. This hypothesis tracking device marks as the first major step in ensuring formal relevance between either sides of an if-then statement. But we're not entirely done just yet. As we'll see, things can get a little spicier. That's my dog, by the way. Yeah, she snores a lot. In relevance logics, a theorem is something one can derive from an empty set of hypotheses. And as we said, standard logic acts as if every hypothesis is a theorem. So if we take the standard proof that if-thens are transitive, it will kind of look like this if we use this hypothesis tracking device we developed for relevance logics. That means that for every formula, be they derived or assumed, they're all going to be treated equally as though they all stem from no assumption whatsoever, and therefore from the same set of hypotheses. Thus, every connective in standard logic is extensional, which means they are mostly designed to link formulas that arise from the same context, the same hypotheses. what relevance logics add on top of extensional ones are intensional connectives, which can handle and synthesize formulas coming from completely different contexts. Thus, intensional connectives technically allow more liberty on the origin of each formula they link together, but doing so also fuses their contexts together in a somewhat irreversible way, akin to Blender. Let me illustrate this with an example. Let's say I have two fictional countries. Let's call them Oberland and Blantree. On one hand, Oberlanders mostly have auburn hair. On the other, Blantreans are mostly blonde. In our analogy here, logical formulas will be observations made inside a given context. So, for example, people having mostly auburn hair applies to context Oberland, while people having mostly blonde hair applies to context Blantree. Now the thing is, if you want to combine these two observations, say for comparison's sake, you will also need to combine their contexts as well. You will state that on one hand, people have mostly auburn hair, while on the other, people mostly have blonde hair. But in doing so, you'd also have to precise that this observation was made by comparing Oberlanders with Blantreans. Let's think about this information for a minute, though. If you're only given the observation that when we compare Oberlanders to Blantreans, we observe that on one hand, people have mostly auburn hair, while on the other, people have mostly blonde hair, would you be able to tell which observation applies to which population? Well, actually, no, because if Oberlanders were mostly blonde-haired and Blantreans were mostly auburn-haired, we will derive exactly the same combined observation with the same combined context. Thankfully, if-then statements help us combine these less trivially by just combining the two resulting theorems. If we look at Oberlanders, then we see mostly auburn-haired people, and if we look at Blantreans, then we see mostly blonde-haired people. Still, it remains that in itself, seeing mostly auburn-haired people on one hand and mostly blonde people on the other, in the combined context of Oberlanders and Blantreans, is more ambiguous as to which observation applies to whom. Therefore, we can think of extensional connectives as food salads. All the ingredients are conjoined, like there are berries, and there is lettuce, and there is cheese, etc. And these ingredients are intact enough for you to extract and sort the various sorts of foods there are. On the other hand, intentional connectives act more like blenders. You sure can blend strawberries with mud, and in the list of ingredients, you would technically have strawberries on one hand, mud on the other. But blending them together into the same smoothie makes it impossible to extract strawberries or mud from it. The only context available in standard logic, even for our hypotheses, is the empty context, the context of theorems. So every connective here is purely extensional, which is extremely important to note. Indeed, at face value, relevance logics can seem weaker than standard logic, but if we only look at what inferences can apply on theorems, all validates every standard one. We'll talk about it more when we talk about rule gamma, but we'll move on for now. In essentially every logic course I've ever attended in real life, focus was mostly pointed towards truth tables. And listen, truth tables are great, but they're a semantics thing. They're really good at showing something is not a theorem, but they're suboptimal, to say the least, if you want to show that something actually is a theorem. It's kind of the opposite from proof systems, which have a hard time showing that something is not valid, while they're very natural to prove theorems. They're proof systems. So, just like standard logic, there is an algebraic semantics side to R with its truth tables and stuff like that, but R most notably comes with a proof theoretic baggage, which is precisely where all of this modeling starts from. So we'll first see what inferences are deemed as inference rules in R and practical extensions thereof, along with the writing practices they yield when writing out arguments in a more natural language setting. The rules that will be presented in this video are mostly derived from V.ii 1984, As we said, every formula is necessarily tagged by a set of indices. Every hypothesis, notably, is tagged by a unique index. So technically speaking, that means hypotheses are stored in a formula-valued function h with an arbitrary domain big T, say, which acts as the set of tags given to say hypotheses. Conclusions, on the other hand, are formulas tagged with a subset of big T, which indicates from which hypotheses they are derived. These tracking tags are mainly used to understand the scope of each formula being derived. In standard logic, I tend to use indenting to tell the scope of each hypothesis, but these tracking tags help us tell which formulas are using what hypothesis in a more nonlinear and frankly natural fashion overall. There are two main structural rules which define how adding hypotheses may impact indexing. The axiom rule states that any hypothesis with tag T entails itself with index set T singleton. This allows the following writing practice. Suppose phi, give it tag T, therefore phi with tag T. This rule helps us call any hypothesis we make within its own scope. The other one is reiteration. Whenever H entails a formula phi with index set P, any extension H star of H entails phi with the same index set P. This allows one to write the following. We have phi with index set P. Now suppose psi, give it tag T, then we still have phi with index set P. This reiteration rule helps us ensure that hypotheses can't destroy previous knowledge, akin to monotonicity in standard logic. However, by keeping track of where that entailed formula comes from, we gain nuance that weakening doesn't really capture all that well. Now, let's get to the operational rules. Unless stated otherwise, every inference step can be prefixed with H entails this or that thing. To prove a conditional, we do so in a similar manner as standard logic does, except we collect our hypotheses from functions instead of sets and stuff like that, so obviously there are going to be some differences. So formally speaking, it goes like so. The sum of maps H with the TA couple singleton entails B, which is itself indexed by the set theoretical sum of P with the T singleton, as to ensure that B actually uses that one added hypothesis. From there, we can derive that H alone entails if A then B with index set P. In a more natural language setting, this will yield something like this. Suppose A, give it tag T. And within this subproof, at some point say, in conclusion, B with index set P such that T itself is in P, so that ensures that deriving B actually used hypothesis tagged T. Therefore, if A then B with index set P minus the T singleton, given we're discharging this hypothesis. Eliminating a conditional is much more straightforward though, as it's a simple modus ponens. If A then B with index set P, A with index set Q, therefore B with index set P union Q. As we're blending contexts together, here P and Q, this makes implication intentional. Which makes sense, honestly, because of course you're gonna need to handle different contexts if you want to say, in this context where we have A, we obtain B, and therefore we discharge the thing so that in the outer context we have A implies B. Yeah, of course you're gonna have to juggle with different contexts here, so it makes sense it will be intentional. To grasp how all of this works a little better, we can look at the transitivity of the conditional to have a look under the hood. We'll use the more usual symbolism for this, using A implies B instead of if A then B, as natural language can get quite unwieldy. Indeed, in formulaic form, this transitivity rule, which is also called hypothetical syllogism, becomes this. It seems benign when written like that, but realizing it as if A then B, then if B then C, then if A then C, makes things much harder to understand than in symbolic form. Okay, so here is the proof. So let's analyze what's going on. We start with no hypotheses, which means our hypotheses are stored in a function from the empty set to the set of logical formulas. Then, however, we suppose A implies B and give it tag alpha. Then, we suppose B implies C and give it tag beta. Finally, we suppose A and give it tag gamma. From there on out, we use hypotheses tagged alpha and gamma with a modus ponens, namely conditional elimination, which makes the conclusion carry the tags alpha and gamma as well. The next step follows a similar logic, yielding our subproof's conclusion with tags alpha, beta, and gamma. Since this concluding formula carries gamma among its tags, we can use conditional introduction, thus discharging hypothesis tagged gamma, restricting the context back to alpha and beta, and giving the proven conditional the index set given by the other hypotheses its consequent used in the subproof, namely alpha and beta. We keep going until we get back to the empty domain function, thus ensuring that the very last formula, this, is actually a theorem in logic R. So that's how you can prove a theorem in logic R using only these two rules. And just like my Crash Course on Formal Logic video, here are some interesting theorems of R you could try to prove as exercises so as to train yourself into using R. And like in my Crash Course video, I will provide solutions at the end of the video. Don't worry. Negation is also a little different as there is no logical constant, unlike standard logic which has the contradiction symbol, for example. Instead, we use the following inferences. Negation introduction goes as follows. If A, then B with index set P. If A, then it is not the case that B with index set Q. Therefore, it is not the case that A with index set P union Q. Essentially, we're saying P and Q are incompatible with A because P tells us A implies B, but on the other hand, Q tells us A implies it is not the case that B, so yeah. Negation and elimination is modus tollens, however. It is not the case that B with index set P. If A, then B with index set Q. Therefore, it is not the case that A with index set P union Q. We also have double negation equivalences that ensure it is not the case that A with index at P can actually replace or be replaced with A with index at P. Once again, there are a few theorems you can try and prove to help you grasp how negation works in that system, like these ones. Remember that conjunction is extensional. It's a salad from which you can extract the ingredients at your will. Conjunction has one introduction rule which demands premises to share a single index set, and two elimination rules thanks to that, which only makes sense because conjunction keeps the common tracking set of either formula. For introduction, we have A with index set P, B with index set P in order to enforce extensionality, therefore A and B from index set P as well. Okay, so that's introduction. Then for its elimination rules, A and B with index set P, therefore A with index set P. And likewise, A and B with index set P, therefore B with index set P. Here are a few theorems that we have in R with respect to conjunction. They're essentially pretty similar to standard logic ones, but with some twists here and there. The fusion of A and B, which is the intentional counterpart to A and B, is characterized as it is full that if A is true, then B is full. It has one very similar introduction rule to conjunction, but which doesn't actually need premises to share the same index set, thanks to intentionality. But its elimination rule doesn't actually extract either formula it connects, as fusing their contexts renders it impossible to tell which comes from which set. So its introduction is A with index at P, B with index at Q, therefore A on one hand, B on the other, with index at P union Q. Fusion elimination, however, is more akin to currying in order to cope with its intentionality. So A on one hand, B on the other, with index at P. If A, then if B, then C, with index at Q. Therefore, C, with index at P union Q. Proving fusion, introduction, and elimination using the actual definition we used for fusion are actually really good exercises on their own. If you want a hint for elimination, you can use the exercises from the negation part to help you with that. It also has the following theorems associated to it. And also, thanks to carrying, fusion helps formulating previous theorems a little differently, though completely equivalently. Essentially, when stating inferences as theorems, fusion helps encode when premises can have different index sets from one another, while conjunction helps encode premises with the very same index set, which will come notably handy when we get to disjunction. Oh, well, would you look at that? Disjunction is the extensional or connective. It has two introduction rules. A with index set P, therefore A or B with index set P. B with index set P, therefore A or B with index set P again. It also has an elimination rule, which is essentially proved by cases, but since it's an extensional connective, it's not completely unrestrained proof by cases. So you have A or B with index set P, if A then C with index set Q, and then, however, we have if B then C with index set Q as well. That's where extensionality kicks in. Therefore, C with index set P union Q. Here, fusion and conjunction are really useful to characterize it formulaically as theorems, because you can see how A implies C and B implies C are linked with a conjunction as they require the same hypothesis set, while this conjunction and A or B, on the other hand, are linked by a fusion as they don't need the same context. As always, some theorems as exercises should help. Given we can characterize material implication, usually noted A horseshoe B, as the formula B or not A, associated theorems are also disjunctive. The most important one is the following, as it basically explains why it would even be considered a form of implication. We have if A then B, then A materially implies B. Okay, that was for disjunction. Now let's go with fission, which is its intentional counterpart. It doesn't have a canonical notation, but I use the turned ampersand because linear logic, mostly. Orally, we say A unless B to say the fusion of A and B, and it is equivalent to if it is not the case that B, then A, which is itself equivalent to if it is not the case that A, then B, thanks to modus tollens, notably. It can be associated to the following inference rules, proved by cases, but completely unrestrained this time. So we have A unless B with index set P, if A then C with index set Q, and if B then C with index set R. Therefore, C with index set P union Q union R. On the other hand, A unless B with index set P. It is not the case that B with index set Q, therefore A with index set P union Q. Here are the last few exercises for R. To wrap up R's proof system, we just need to add one more rule, namely distributivity of conjunction over disjunction. Let's say we have A and either B or C or both with index sets P. Therefore, either A and B or A and C or both with index set P as well. So that's it for R, at least it's natural deduction, but there are extensions that will help us treat quantifiers and equality as well. RQ is the extension of R which adds quantifiers. There's nothing much new under the sun compared to standard logic. We have generalization and instantiation rules, which respectively act as introduction and elimination rules. And they're essentially the same as in standard logic, except we add different index sets to each premise and combine them with their union in the conclusion. The only things that get added on top of them are distributivity rules. So universal quantification is quote-unquote distributive over disjunction. So For all x, either a or a of x or both with index at p, x does not occur freely in a, therefore either a or for all x, a of x with index at p, once again. And likewise, conjunction is quote-unquote distributive over existential quantification. So a, and there exists x such that a of x with index at p, x does not occur freely in a, therefore there exists x such that both a and a of x with index at p. In mathematics, we don't usually say for all x or there exists x. We usually say for all x in E or there exists x in E each time we bind variables that range over a given set. So what does it mean that for all x in E, a of x? Well, that's actually shorthand for all x, if x is in E, then a of x. And if we want to preserve conversion of quantifier rules, which are essentially a bit like De Morgan rules but for quantifiers, that would mean that there exists x in E such that a of x would have to be there exists x such that we have the fusion of x in E and a of x. So the main theorems we want to prove using these definitions are, well, conversion of quantifiers. As Brady in 1984 only talks about quantified relevance logics, we need to step outside of it just a little bit to talk about equality in relevance logics. So there are quite a few sources, and they sometimes diverge a little bit on subtleties, but overall they seem to gravitate towards the rules I'm going to show you. So the first three ones are just the regular equivalence relation axioms, or rules rather. So you have t equals t is a theorem with a term t. Terms don't have to be variables, they can be expressions like, x squared plus 1. That is always equal to x squared plus 1, so that's fine. Another axiom of equivalence relations is that t1 equals t2 implies t2 equals t1 regardless of terms t1 and t2. That is the axiom of symmetry. And the last axiom, the axiom of transitivity, states that if you have t1 equal t2 on one hand, t2 equal t3 on the other, then t1 equals t3. So these are the three main axioms you want for an equivalence relation, and obviously you will want them for equality. But there is one last thing we need to really talk about equality. In standard logic, we have the equality elimination thing, which tells us, well, if you have t1 equal t2, and you have a of t1, then you have a of t2, right? Well, in relevance logic, obviously we have this, plus the indexing stuff shenanigans, plus the fact that A has to be a relevant predicate. So, what does that mean? Well, essentially a relevant predicate is one such that when you say A of X, it actually does really depend on X. The way we formalize this exactly is that for all X, if A of X, then for Y, if X equals Y, then A of Y. So yeah, relevant predicates are a very important thing when we talk about relevant identities. In mathematics, the main two systems currently are standard logic and intuitionistic logic, which is notably used in proof assistants like Lean or Coq, even though they do have standard libraries on top of them, but the calculus of construction basis is intuitionistic, so yeah, there's that. So one may wonder, can we do mathematics in relevance logic as well? And the answer is surprisingly yes. There's no catch to that. I mean, there are some, but it's just don't usually see that all that much. So, but we can definitely do this. So let me show you. we will show that the square root of 2 is irrational using RQ style writing. The crux of the proof, for those who haven't seen it yet, is the following. First, we'll show that the square root of 2 cannot have a simplified fraction. However, if the square root of 2 were a rational number, then the square root of 2 will have to have a simplified fraction. So by most tokens, we will be able to conclude that the square root of 2 is irrational. So that's the usual proof we see in textbooks, except it's going to be written with a bunch of tags here and there to understand the scope of each hypothesis we make along the way. Okay, so we'll suppose that P0 is an integer, and we're going to tag that 1. Then we suppose that Q0 is a non-zero integer, tagged 2. I say non-zero because it's going to be the denominator of our fraction. And finally, we're going to suppose, for contradiction's sake, that the square root of 2 can be written as P0 over Q0, and we're going to tag that 3. Okay, we do have the square root of 2 equals P0 over Q0, which carries tag 3, because it's hypothesis 3. From there, we can do a bunch of algebraic manipulations to derive that P0 squared is actually equal to 2 times the square of Q0, which itself also carries tag 3. Now let's look at 2 times the square of Q0. As we know, Q0 is an integer. That one was hypothesis tag 2. Hence, Q0 squared is also an integer, and this assertion also carries tag 2. Therefore, twice the square of Q0 is an even integer, and this assertion carries tag 2. Okay, now let's come back to P0 squared. As we said, P0 squared is twice Q0 squared. That one carries tag 3. And we just proved earlier that twice Q0 squared is an even integer, which carries tag 2. Therefore, P0 squared itself is an even integer. And there, we need to carry both the tag 2 and the tag 3. Now we know that P0 squared is even within scopes 2 and 3. Now, we also know that P0 is an integer. That was our hypothesis tag 1. Therefore, P0 itself is even, which carries tags 1, 2, and 3. The fact that P0 squared being even and P0 being an integer yields that P0 itself is even is an interesting proof in and of itself. It's usually done with contraposition, but there's been a meme recently which shows how you can do it without contrapositive. So yeah, that's a very funny sidetrack, but we're gonna stay on the proof that the square root of 2 is irrational. Okay, now P0 is even. That one we just proved using tags 1, 2, and 3. Therefore, there exists an integer k such that P0 can be written as twice k. So this one also carries tags 1, 2, and 3 because it uses P0 being even. Okay, so let's suppose that k0 is an integer, which we're going to carry with tag 4, and then we're going to suppose that P0 is twice k0, which will give tag 5. Now recall that the square root of 2 is equal to P0 divided by Q0. That was our hypothesis tagged 3. And now we also supposed that P0 is equal to 2k0, which is hypothesis tagged 5. Therefore, Q0 squared is equal to twice the square of k0, which itself carries tags 3 and 5. So Q0 squared is equal to twice the square of k0, which carries tags 3 and 5. We also supposed that k0 is an integer, hypothesis 4. K0 is also an integer, hypothesis 2. Therefore, Q0 is even using all of these tags at once, 2, 3, 4, and 5, as we showed for P0. Now, given that P0 is even, using tags 1, 2, and 3, and given we just showed that Q0 is even, using tags 2, 3, 4, and 5, we derive that P0 over Q0 is not a simplified fraction, as both the numerator P0 and the denominator Q0 are even integers. And this assertion that P0 over Q0 is not a simplified fraction uses all the tags at once. 1, 2, 3, 4, and 5. Before we can stop here and use motor zones to argue rational numbers always have a simplified fraction, which clearly the square root of 2 does not have because of what we just said, we have to proceed step by step very cautiously to discharge each subproof one by one. Well, we can do in bulks, obviously, using fusion and stuff like that, which we're going to do so that it makes the proof a little less tedious, but still. So in discharging the two previous subproofs simultaneously, we have that if k0 is an integer on one hand, p0 is twice k0 on the other, then we have that p0 over q0 is not a simplified fraction by conditional proof, and this assertion will carry tags 1, 2, and 3 only because we discharged tags 4 and 5, and also because the conclusion itself used tags 1, 2, and 3. Now from there, we see that k0 doesn't occur freely among hypotheses tags 1, 2, and 3, and k0 does not also occur freely in the following sentence. If k is an integer on one hand, p0 equals 2k on the other, then p0 over q0 is not a simplified fraction. Therefore, for all integer k, if p0 equals 2k, then p0 over q0 is not a simplified fraction, using universal generalization. This one also carries tags 1, 2, and 3 as it's derived from the previous thing we just said. So since there exists an integer k such that p0 equals 2k, and that for all integer k, if p0 equals 2k, then p0 over q0 is not a simplified fraction, using tags 1, 2, and 3, and also, finally, as k does not occur freely in the sentence that p0 over q0 is not a simplified fraction, we can use existential instantiation to derive that p0 over q0 is not a simplified fraction, using tags 1, 2, and 3. Now we can discharge all the previous subproofs simultaneously by stating that if p0 is an integer on one hand, q0 is a non-zero integer on the other, then if the square root of 2 is equal to p0 over q0, then p0 over q0 is not a simplified fraction by conditional proof. And then we can use universal generalization again, similarly to how we did it previously, so as to say that therefore for all integer p and for all non-zero integer q, if the square root of 2 is equal to p over q, then p over q is not a simplified fraction. This formula can also be more concisely said as the square root of 2 has no simplified fraction. And here we can bring, if the square root of 2 were rational, then the square root of 2 would have a simplified fraction. However, the square root of 2 has no simplified fraction. Therefore, the square root of 2 is irrational by modus tollens. And there, we've proved that the square root of 2 is irrational. Obviously, I was being a bit meticulous here because I wanted to use the exact rules I showed you, but for reals, it would probably just look like this. Obviously, it's gonna be a bit lengthy, but it just looks exactly like the usual proof we have for the square root of 2 being irrational. In order to study relevant mathematics more exhaustively, relevance logicians have proposed several systems. The most notable ones are the relevant arithmetic systems R-sharp and R-double-sharp. Without going too much in depth into those, the most important problem that logicians tend to verify with such axiomatization, above consistency, is the admissibility of Ackermann's rule gamma, the latter of which I'm going to explain right now. So as you know, modus ponens goes like this. If A, then B. A, therefore B. Ackermann's rule gamma is what you get if you replace that if-then statement with the material implication instead. So A materially implies B, A, therefore B. Though modus ponens is thankfully valid in R, Ackermann's rule gamma is not, which is a prime consequence of material implications extensionality here. However, there is quite a remarkable fact, which is that though Ackermann's rule gamma is not valid, it is admissible in R and RQ. What this means is that in both of these systems, as well as a lot of other relevance logics, if A materially implies B is a theorem, specifically, and A is also a theorem, then B must also be a theorem. So more generally, a rule is admissible when the conclusion is necessarily a theorem whenever both premises are, which contrasts with validity, which doesn't require theorems to be premises. Also, for that matter, standard logic treats every hypothesis as a theorem. It holds that every admissible rule of standard logic is a valid rule in standard logic, which is why we don't see that distinction being made all that often, and also why I had a hard time wrapping my head around it, but I digress. The admissibility of rule gamma essentially acts as the ultimate frontier we need to reach if we hope to encode standard logic extensionally within these relevant systems. If the admissibility of rule gamma failed, that would mean our system is truly weaker than standard logic. And unfortunately, rule gamma is indeed not admissible in R#. Historically, that was the first seriously proposed relevant system that had this failure. So that came as quite an unpleasant surprise. An extension of R#, simply called R#, thankfully does render gamma admissible. While standard logic is quote-unquote equivalent to Boolean algebras, R is quote-unquote equivalent to De Morgan monoids. This result generalizes quite naturally to its quantified extension on Q, as shown in Meyer, Dunn, and Leblanc, 1974. Relevance logics generally use routley-meyer models, but the Morgan monoids at least form a setting quite familiar to that of Boolean algebras and truth table stuff, so it's much easier for me to explain how it actually functions. Still, before we get into the technicalities, which I can't really explain without appealing to a solid background in mathematical logic, lattice order theory, and abstract algebra, I'm going to try to motivate you thanks to what it actually implies. First and foremost, it is important to note that every theorem of R is a theorem of standard logic, but not the other way around. Algebraically, this translates in the fact that every Boolean algebra is essentially a form of the De Morgan monoid, where fusion and conjunction are one and the same. And thanks to De Morgan monoids, we can tell apart which standard theorems are not theorems in R. As I said earlier, truth tables and other such semantic stuff are really good at showing that formulas are not theorems, contrary to proof systems which are better suited for, well, proving theorems. In particular, there's this really handy De Morgan monoid that Rosek and Tether 2026 call the crystal lattice, which is a 6-valued De Morgan monoid which you can use to disprove every paradox we showed in the first part of the video. You can also toy with another 10-valued De Morgan monoid. I don't remember its name, I think it's C6 or something like that, but it's on the many-valued logic playground, or MVLPG for short, which is a tool I made a while ago to ease the study of many-valued logics, akin to tools like Magic or the VS Pursuer, which the aforementioned paper presents, except MVLPG is directly available online, no installment required, and no PC required either. That's not promotion, that's shameless self-plug, by the way. So as I said, that Rosek and Tether 2026 paper is also quite relevant for this part, because they mention that by studying this crystal lattice model for R, we can show R satisfies the variable sharing property, or VSP for short, hence why their software is called VS Pursuer. Haha. The VSP essentially says that any conditional theorem has to have its antecedent and consequent share a common propositional variable, which, ironically enough for it being mentioned in the last part of the video, is the main thing every relevance logic needs to satisfy. To be very clear though, R has been shown to satisfy the VSP since like the 70s, I think, or maybe maybe even the 60s, I'm not sure. So it's nothing new, but that 2026 paper lays out a proof I find much easier to sit through, because it's incredibly short for such an important property. As a foreword, Boolean algebras are not necessarily two-valued. Boolean algebras are lattice-based tuplets, b less than or equal, in which b serves as a set of truth values, less than or equal as a lattice order relation. There are Boolean algebras with 4, 8, 16, 32, or any power of 2 as their number of elements. More generally, Boolean algebras can be written as power sets of a given set, which explains why it's powers of 2, and also explains why there is no countably infinite Boolean algebra. There has to be uncountable if it's infinite. But anyway. Moreover, every Boolean algebra, including the two-valued one, can be readily interpreted as De Morgan monoids, which means that De Morgan monoids are actually a more general structure than Boolean algebras. A bit like hating algebras, but they're two completely different branches in a way. So, let's see what a De Morgan monoid actually is. So, a De Morgan monoid is defined as a full tuplet, E, circle, less than or equal, not, where E is a set of truth values, circle serves as an algebraic fusion operation, less than or equal serves as an order relation, and not serves as an algebraic negation. Similarly to how Boolean algebras are defined in a lattice theoretical way, such a De Morgan monoid is defined using the following properties. E circle is a commutative monoid. E less than or equal is a distributive lattice. Not is an unary operation on E. And then we have a bunch of axioms, which I'm just going to put on screen. Honestly, I don't want to bore you. There's the upright idempotence one, the double negation one, the contraposition ones. There's also distributivity of circle over join operations, and also currying, obviously, which is also called residuation in this context. I mean, it doesn't show all that much here, but we define x right arrow y as the negation of x circle the negation of y, just as it's written in this last axiom. So instead you can write it like so, and yeah, you can see it's just currying. We can also define x turned ampersand y as not the circle of not x and not y. That's just the De Morgan dual, in a way, of the circle. Now, to understand how these provide models for R, we need to understand how these De Morgan monoids provide interpretations for logical formulas. This way we can define an E circle less than or equal not interpretation as a function I from logical formulas to E, which satisfies the following properties. As announced, for any formula phi, we have that phi is a theorem of R if and only if we have this thing. The main formula being 1 being less than or equal to I of phi. Akin to how we need to have the top value being equal to I of phi instead in the case of Boolean algebras. Because in Boolean algebra, De Morgan monoids, the circle is just the meet operation. And what is the identity element of the meet operation? You guessed it, it's the top value. This also means that we can easily translate the De Morgan monoids into truth functional semantics, where designated values are precisely the values of the underlying set that are greater than or equal to the circle's neutral element. So, what should we do with standard logic? Should we throw it away completely in favor of relevance logics? Well, no, okay, let's add some nuances here. Though relevance logics are a much finer and, in my opinion, robust model of reasoning, we can still use standard logic as a more introductory setting, of which we must acknowledge the limits. If we want to compare this dynamic with something a bit more well-known, it's a bit like how we still teach Newton's theory of gravitation introductorily, even though we have the theory of relativity, which gives much better predictions, especially in edge cases. Those said edge cases are pretty important, like, Mercury's trajectory or black holes and stuff. In this case, Standard logic's limitations appear whenever a math test asks, for example, to deduce thing A from thing B. It's generally expected that you should explicitly use B in order to even reach A, and it doesn't suffice to prove thing A independently and then argue it can be deduced from thing B afterwards, thanks to monotonicity or positive paradox, what should I call it. This will technically be correct in standard logic, but relevance systems like R make such deductive questions much less trivial and much more sound pedagogically speaking. Standard logic can be kept as a broad model that serves for lots of purposes, but I don't think it should be given a status of absolute be-all and end-all of formal reasoning like some didacticians or mathematicians seem to argue. I would argue, however, that it would be nice to at least see relevance logics being taught at more advanced levels and for mathematicians to start using them a little more often. Which I think we would if some relevance logic did become the basis for, say, a proof assistant, given proof assistants are getting quite the hype recently. Relevance logics, thanks to its rigorous mechanisms, help cure many false positives of standard logic. It also has very little false negatives, at least if you don't try to mix sets of operations in a very unwieldy way, as it gives very unpredictable behavior, a bit like when you make problems that mix primality and additive formulas. That usually doesn't end well. You get Gauss conjecture, you get a bunch of stuff like that that are really hard to solve. So mixing in intentional and extensional interpretations of different natural language connectives can be a bit problematic, to say the least. However, if we want to go further, there are very important false negatives that many studies show are held by a majority of people in a myriad of contexts. Namely, Aristotle's thesis, which essentially ensure the falsity of having a proposition imply or be implied by its own negation, as well as Boethius' thesis, both of which essentially say if one proves if A then B, then it's not the case that if A then it's not the case that B. These two theses are associated to another family of alternative logics called connexive logics. However, Routley, Plumwood, Meyer, and Brady in 1982 showed that if you add these connexive theses to most relevance logics, then it becomes a theorem that, regardless of A and B, we have that it is not the case that if A then B. In other words, every conditional becomes quote-unquote false. It doesn't necessarily make the logic trivial, though. The relevant entailment logic E, for example, notoriously has a three-valued connexive truth functional model, which does also treat every conditional as false. But more importantly, it does have non-theorems. It is non-trivial. It's just glutty, that's all. You can also toy with this connexive three-valued model of E on MVLPG, by the way. Just so you know, I didn't find Routley, Plumwood et al.'s 1982 work, but this exact result was reported in Tether 2025 if you want further information. It should be noted that there are some really interesting connexive relevance logics. There's a really cool talk by Gemma Robles, which is thankfully out here on YouTube, and showcases a bunch of extensions of IV.ii with connexive VSP witness and conditional matrices. So essentially, relevant connexive logics. They can make it so that the conditional is not irreflexive and thus avoid the usual connexive relevance logics problem that Routley, Plumwood et al. Described in their 1982 work. What's weird though is that at least some of them, I didn't test them all, but some of them at least can validate the reciprocal Boethius thesis, akin to standard logic. Because of this, it makes it so that fusion and implication become essentially the same operation, which I'm not sure how I feel about. One of our matrices is what I use on MVLPG, again, as the scroll bar link for IV.ii, which if you want to play with this sorts of stuff. But still, like many logicians in these alternative logics fields, I do frankly believe the future of relevance logic and connexive logic alike will require combining the two to form a much more truthful model of logical reasoning. Thanks a lot for watching. Please comment down below if you want more details.